Hi, everybody. Welcome to the second of three mini lectures on climate change mitigation. This time we're going to focus a little bit on the money side of the problem. So, as you may be aware, the UN a couple of years ago came to an agreement that in order to prevent the worst elements of climate change from causing global problems, we needed to keep the amount of global warming that we cause to under 2 degrees C. I should emphasize that this is not 2 degrees above where we are now. This is 2 degrees C above the climate before the Industrial Revolution. So since we've already seen almost degrees worth of global warming already, that means we've only got a degree and a little bit left to go before we run out of room. Um, so, looking at these projections that I showed you last time for the different warming that we would be likely to see in a bunch of different scenarios for human activity, from the 2.6 to the 8.5 scenario, we can see that in order to keep CO2 low enough that we stay below 2 degrees C, we need to follow the 2.6 pathway, or maybe the 4.5 and get really, really lucky. It can come close if things work out. So in order to do that, like I said, we need to follow the RCP 2.6 or 4.5 pathway. So let's take a look at what that means in terms of our CO2 emissions over time. So on the left is a graph of future projections for CO2 emissions for each of these four different visions of the future. Business as usual, blue curve goes up and then starts to tail off at the end of the century. Green curve involves almost a rapid cut. This is 2.6. To follow that curve, we need to cut emissions by about 40% by the year 2030. All right, that's 10 years from now. A 40% reduction in fossil fuels. Wow. Um, 2030 seemed like a while ago when I first started teaching this class, but it's really coming up quick. And by 2100, to follow the RCP 2.6 path, greenhouse gases need to be essentially zero. We need to 100% completely decarbonize our entire economy. So that's a heck of a tall order, and we need to think about the degree to which that can be achieved, how we can get that done, what we need to focus on, and how it's going to work. I want to emphasize one thing, which is right now, human emissions of CO2 are rising almost exponentially. And it's not enough for us to bring them under control and cause them to flatten out and level out. We need to actually bring those emissions down below where they are now, down below where they were in 1900, all the way to zero, is basically what this is saying. All right. A metaphor that's often used is like filling a bathtub. You can think about a bath, the CO2 presently in the atmosphere as being the tub, and human emissions as being the faucet. All right. If you leave the faucet turned on, the CO2 in the water in the bathtub is going to continue rising until the amount coming in equals the amount going out. But basically, the tub's going to keep on filling unless you actually turn the tap off. So, yeah. So, how are we going to go about doing that? All right. And what's the protocol? The challenge that we face in thinking about the economics of this, and I am not an economist, so my understanding of this may be worse than yours. But the point is that some of the things that we can do are super cheap. In fact, some of them will actually save money while also helping the planet. That's awesome. But once you've run out of the cheap, easy, low-hanging fruit, if you want to get more reduction in CO2, you're going to have to spend more and more money on more and more expensive projects. The sensible thing to do is to start with the cheapest ones and work your way up. But we need to think about how much a given amount of CO2 prevention is going to cost us. There are two key vocabulary words, two key ideas involved in thinking about this. The first is what we call the carbon price. All right. This is how much do we need to spend on implementing some technology or doing something in order to avoid emitting 1 ton of CO2 into the atmosphere. So this is an amount in dollars that it costs to avoid emitting 1 ton of CO2. Okay, I'll give an example in a minute. Mitigation potential, on the other hand, is in the total number of gigatons per year that you can cause by doing that particular thing. All right. So carbon price is about how much it costs, and mitigation potential is how much it can do. So a simple example, LED lighting has taken over the world in a really short amount of time. They're more expensive than traditional incandescents, but they last longer, so you don't need to buy as many, and you pay less in electricity. Overall, the net savings after you pay for the LED and then save for the electricity and not have to buy so many bulbs is something like $100, which is to say, in the long term, when you buy an LED light, it pays you $100. And you avoid emitting something like 400 kilos or 0.4 tons less carbon dioxide over the lifetime of the bulb. So the carbon cost is going to be negative $100 divided by 4/10 of a ton, which works out to about negative $250 per ton. All right, so that's not a cost, that's a savings of $250 for every ton. You're doing well by doing good. All right. Now, the mitigation potential of this can be estimated by looking at, okay, suppose we deployed LED lights and completely replaced all the other kinds of lights in the world. Incandescents are extinct. The mitigation potential would be 0.4 tons for each light bulb times the number of light bulbs in the world. But here's the important thing about mitigation potential is you can't, there's a limit. All right. Imagine that we went and replaced all the light bulbs in the world with LEDs, and then we wanted to save more carbon and cut emissions by even more than that. Well, somebody could say, well, if we saved so many gigatons by buying a bunch of LEDs, if we buy twice as many LEDs, we can save twice as much greenhouse gases. No, that's not how it works, right? The LEDs are plugged in, and once you've replaced replaced a light bulb, you can't replace it again and get double the savings. That's dumb. All right. So the point is, once you've done all the LEDs, you have to move on to a different technology, maybe hybrid cars or insulating buildings or something like that. The point is, every given technology has a certain amount that it can mitigate CO2 release and a certain cost for doing that. That cost can be negative or positive. But once you've used a technology and deployed it in full, you got to find another thing to do. So a couple of examples of carbon prices, and these are a moving target, all right? So suppose we took all the existing coal power plants and replaced them with nuclear power plants. Nuclear power doesn't produce fossil fuels, so that's awesome. Nuclear power ain't cheap though, but you don't have to pay for fuel. So yeah, it's a trade-off. Various people have done the estimates, and replacing with nuclear power plants might have a slight negative cost or a slight positive cost. It's kind of near zero-ish. Replacing coal power plants with gas power plants, this is actually an old slide that I left in on purpose. The estimate used to be that gas was more expensive than coal, and so the switchover would cost money. As I said, gas is a cleaner burning fuel, less CO2, so you can get some savings in save the planet, but not necessarily save any money. But now, thanks to fracking, the cost of natural gas is actually less than coal, and so that's why coal power plants like Brighton Point are going out of business. It makes good business sense to get rid of coal power plants and replace them with natural gas plants. It does the environment a favor, a limited favor, and it also ends up being cheaper. So it has a negative carbon cost now. Replacing fossil fuel plants with wind power, it depends on where you put the wind power. If it's in very windy places, the costs can actually, they can pay for themselves. But in less optimal locations, which are places we're going to have to use in order to make this work, there can be a substantial positive carbon cost. And that carbon capture and storage technology that I talked about is really quite expensive. All right, just to give a sense of what these carbon costs mean and how to compare them. A year ago, the cost of enough oil to create 1 ton of carbon dioxide was about $130. So we're talking about, with carbon capture and storage, um, increasing the cost of power by something like 30%. I should emphasize, though, that these oil prices that I'm relying on are from before the COVID-19 crisis. During the COVID-19 crisis, as I give this lecture, oil prices are basically zero. You can have as much oil as you want for free. Just take it off their hands, please. All right. Anyway, but enough about that. All right. So the point is that these costs are pretty significant compared to raw fuel prices. But the US is able to produce something like $3,000 of GDP for every ton of CO2 that it emits. So these costs are relatively manageable compared to that. All right. So once again, carbon cost, how many dollars it takes to avoid emitting a ton of CO2. Mitigation potential is how many tons of CO2 you can save by deploying that technology completely. So here's a rather complicated graph that sort of takes a bunch of technologies and considers them in order from the cheapest carbon cost to the biggest carbon cost. For every one of these, the vertical axis indicates its carbon price, and the width of the bar indicates its mitigation potential. All right, and mitigation potential is in megatons here. And so the point is that, say, for example, replacing gas vehicles with hybrid gas vehicles. All right, that's a negative carbon cost. You actually can save money by doing this, but its mitigation potential is quite small because it doesn't save a whole lot of fuel. So we need to look at more expensive systems. This has ordered them in order from negative carbon cost to positive, and you can see that there are a bunch of technologies like LED lights or hybrid vehicles that save you money while also protecting against greenhouse gases. That's good, but in order to reduce our emissions by 40% by the year 2030, we need to reduce our CO2 emissions not by 2, 3, 4, 5%, but by 40%, which is all the way on the right-hand side of the graph. So this graph gives us a potential idea of the order in which we should adopt technologies. But the point is that we need to do all of them. I want to point out a few highlights here. Wind power can have kind of a neutral cost. Better, more efficient buildings can save a lot. There's a lot of potential for wind power in sites where it's not necessarily the most ideal, but that would end up being significantly more expensive than our current power sources. Plug-in electric vehicles ain't cheap. Residential photovoltaic is really not cheap compared to the amount of power it produces. You can get some rebates from the government, but in the end, we all pay for that. So this is maybe not the first option you should consider, but it's among the options that you're probably going to have to consider. And finally, carbon capture and storage, abbreviated CCS, are a full fleet of these very expensive and really relatively high abatement potential technologies. And it's actually very difficult to get up to 40% without adopting all of these, including carbon capture and storage, continuing to burn fossil fuels, but burying your waste products. All right, so the point is that while some renewable technologies can save us money, in the end, this is going to end up costing us more than business as usual. We're going to have to deploy some expensive technologies in order to get this under control. And most of us think it's going to be worth it, but we should not pretend that the cost is going to be zero. In any case, in order to make sufficient cuts to reach this RCP 2.6 pathway and keep global warming under 2 degrees, we're going to have to consider technologies that have a carbon price of up to something like $100 per ton of CO2, which is almost on par with, comparatively, with the cost of oil when I wrote this last year. Point is, we may be looking at something like doubling in gas prices, maybe a doubling in your electrical bill in order to get a handle on this. So how are we going to do that? What are the politics? I try to steer away from politics, but I do want to focus on one potentially interesting technology. Ideas we can use, which you've seen promoted by all kinds of politicians, are things like banning and restricting dirty technologies and funding and helping promote and give tax incentives for green technologies, which is great. The problem is that, in my personal experience, government is a powerful force for good, I think, but it's slow. And it can't always keep up with rapidly changing technologies and changing costs. If the government is in the business of promoting particular technologies, then there's a huge incentive for lobbyists and big corporate interests to take advantage of that process and make sure that it benefits their industry rather than anybody else's. And while we all know that fossil fuel companies do this on a daily basis, we shouldn't discount the fact that green energy technologies are competing against each other and against the fossil fuel companies, and their lobbyists we can expect to be no less hardball than anybody else's. In any case, there's a real potential for corruption, bribery, and other problems if the government is in the business of picking which technologies can succeed and which must fail. So the way I think about it, and this is only my personal perspective, I wonder if there's a way for governments to coax the free market into working for the environment rather than against it. All right. Capitalism and the free market are powerful and dangerous tools, but perhaps they can be provided with incentives to do good instead of evil. Maybe you think I'm naive, but I want to talk about this idea. Carbon taxation, in particular, for political purposes, the revenue neutral version of carbon tax. So basically, here's how it would work. When fossil fuels are pulled out of the ground and sold, everybody who produces them would have to pay a tax. That money would be collected by the government, and that would increase the cost of fossil fuels, all right? And that money that was collected would be returned back to the people as a dividend payment. California is already doing this, and a few other European countries, but it could be enacted as a wider spread position. In any case, the point is that on average, the money goes back to the people, and there's zero net benefit. But this increases the cost of dirty technologies and reduces the cost, relatively speaking, of renewable technologies. So if fossil fuels were cheaper than wind power before, fossil fuels may now be more expensive than wind power, and the money comes back into your pocket, so you have more money to spend on the cheaper renewable energy. There are some really big advantages to this. First, the price changes that we see trickle through the economy. And so not just the fuels themselves, but everything made with the fuels also costs more. And so every company in America has an incentive to use greener products just because they're cheaper, right? And companies that are more effective at using green power, green technology, save more money and are able to pass those costs on to all savings onto the consumer, with the net benefit that everybody wins by buying renewable technologies and things made with renewable power. The really great advantage, as far as I'm concerned, is that customers or the government don't need to figure out which is the greenest possible option. All you have to do is buy the cheapest thing and be sure that in the background, the carbon taxes are making sure that the more expensive one is more expensive because it's more heavily fossil fuel taxed. I should mention that a lot of people have problems with the word tax. This is sometimes called a carbon dividend in reference to the money coming back to the people. Is to focus on the kind of upside instead of the dirty word tax. By the way, I should say that this is not the only option. If you would like, you can also imagine doing a carbon tax and then using the money that you gain to build infrastructure, improve transportation networks, you name it, instead of giving it back to the people. But the important thing is that you make fossil fuels more expensive. All right, so that's it for my second lecture. Next time I'm going to be talking about something called the Kaya identity, which will help us get a handle on why exponential growth is leading to problems. Well, that wasn't a good explanation, but you'll see. Anyway, stick with me.